Move button. There we go.
Hey, Mr. Cunningham,
Yes, sir.
I'm not for sure, but it's storming out right now. If something happens and it cuts
Gotcha.
out,
I actually,
you
I
know.
meant to say the same thing. I heard thunder outside. My power tends not to go out, but it has. I've never actually had it go out during a live class before. I did have my internet go out one time, I think, prior to a class, but that's it. So, if anybody, if I lose anybody, I know we got storms going on, so power, you may lose power. So, and the same thing for me, as I said, if all of a sudden I'm gone, that's what's happened. So hopefully that doesn't happen. All right. So 4B. Last section of chapter 4, and we're then going to be ready, looking at taking the test and moving on to statistics and some probability. So 4B is called power compounding. All right. So, and looking at the mathematics behind it. All right, now. All right, so I'm not going to write this down, but per se, that's supposed to be an N. So when I talk about principal, that's the amount of money that you would personally invest yourself, or amount of money that starts in an account. Right? So now, or the principal is the balance on which interest, and that's what this is all about, is what we call interest is paid. All right, so when you put your money into, let's just say a savings account, and it's in there, you're making money off that, a percentage of whatever your principal is, whatever you invested. So that amount times the percentage, whatever the rate is for that particular savings account, then you earn that much more money for just leaving your money in the bank. Now, two kinds of basic interest, what we call simple, and then what we call compound. All right, so simple interest is paid only on the original investment. Whatever you initially put into the savings account, into CD, whatever, and but only on the original investment, not on any interest added at a later date. Now, compound interest is paid on both the original investment and all interest that has been added to the original investment. Okay, so as an example, and this is just going to be simple interest. So let's just say you invest $1,000 in some sort of savings account. And this is your principal. I'm sorry, guys. I gotta try to go shut this dog up. All right, so you invest $1,000 and you've got 5% interest. And this is going to be simple interest. So usually it's annually, which means every year. So at the end of that first year, figure up how much you earned, take the percentage, write it in decimal form, 0.05 times $1,000. And that's going to come out to be $50. Right, so that's what you have earned. And let's say you do that for 3 years. If it's simple interest, then you're only every year getting $50. Because you're only going to, every year, you're going to multiply 0.05 times your original investment. That's it. So after 3 years, you earn $150, or that is 3 times the $50. Right now, so you can say your investment grew from 1,000 to 1,150. Right now, let's compare that if it was compounded. Right. So you put in your $1,000, and from now on, capital P is principal, and that's what it'll be in the formulas we're going to look at tonight. So still 5% interest, but this time it's going to be compounded. So after 1 year, you still would earn 0.05 times 1,000, and which is going to give me 1,050. After the second year, this is how it's going to differ than simple. You're going to go 0.05 times your interest earned as well as the principal. That is times 1,050, which comes out to $52.50. And so after the third year, it would be 0.05. Now you're going to take your 1,050 plus the 5,250. The interest that you earned in that second year, that comes out to $1,102.50. So it's 0.05 times that. And so that's going to come out to be $55.30, or excuse me, 13 cents. Okay, so if you then take your $1,102.50 plus your new interest earned for the third year, $55.13, you're going to have a grand total of $1,157.63. So what are you chewing on? What are you chewing on? Oh, gosh, dog. Lay down, go sleep. All right. You would have earned, since with simple interest, you earned 1,150. Here you earned 1,157.63. You would have earned $7.63 more using compounded interest. As compared to simple. All right, which doesn't seem like an extreme lot of money. However, the numbers certainly would dramatically change if you had a lot more money than, say, $1,000 in there. The moral of the story is it's better to compound. So you're gonna, over time, you're gonna earn more money than if you just use simple interest. Any questions so far?
I don't think so. I'm good.
All right. So that's really what we want to investigate mostly here is compounded interest. It's definitely, it is, you're going to earn more money in doing that. Now, what would be nice is if I had a formula that I could put in my interest rate, my principal, the number of years that I want to look at it being in that account, and what my interest rate is, whatever, 5%, 6%, whatever, and just have a formula. And so that way, if I have a 20-year investment, I'm not having to calculate it like I did here. All right, so what might some formula look like? So let's do another example. And what we're going to look to do is try to build a formula, a compounded interest formula. All right. So oh, okay. So I had skipped over this. This is actually kind of a cool little and true story. So I'm just going to read you this. Then we're gonna use this particular example to build this formula. So on July 18th, 1461, King Edward IV of England, a long time ago, borrowed the modern equivalent. So remember CPI, Consumer Price Index table, figure up current prices based on, anyway. So the modern equivalent, today's dollars, $384 from New College of Oxford. So it says the king soon paid back 160, but he never repaid the remaining. We're going to find where we're going to start. $224. He never repaid it. The debt was forgotten for 535 years. So in 1996, they discovered that the king had never repaid this debt. And a new college administrator wrote the Queen of England asking for repayment with interest. Assuming interest rate of 4% per year, the administrator calculated at 4% over 535 years, the college was owed $290 billion. Power of interest. So unfortunately, there was actually no clear record that he ever legally had to repay it. And but it does illustrate the power of compounding. All right, so we're going to take that $224 and see how perhaps the administrator at this College of Oxford arrived at the $290 billion owed. All right, so so this was going to be over 500. This was the debt that was owed. Time would be 535 years. And assuming 4% interest. All right. So end of year one, back in 14, whatever that was, then that would be 224. Now, if I do this times 1.04, what that's going to give me is actually, so it's by doing that, notice if you take 4% itself, write it as a decimal, that's 0.04. If I add in 100%, it's the same thing as if I went 224 times 0.04, got that result, and then added that back to the original amount of 224, like I was doing in that previous example. So basically, if whatever the percentage is, if I add 1 to that and multiply it there, I'm going to get exactly how much money you have, principal plus interest, is my point. So it comes out to 232.96. Okay, so now just to illustrate again what I did there. if I had taken 224 times just 0.04, that's going to come out to, calculate that. Uh, 224 times 0.04, $8.96. And then 224 plus 8.96 is, as we thought it would be, 232.96. Right. So a simpler way to calculate this. Are we okay with that? All right, so
Yeah.
now what we're going to do is we're going to be looking for a pattern here. Looking for a pattern that we maybe could build a formula with. So into year 2, I could think of it this way, the 224. Now, when you went times 0.104, that gave me how much money I had in the first year. The second year would be this amount times 1.04. So instead of doing that, I'll go 1.04 times 1.04. That is, just multiply it by it twice. Now, that's going to come out to be, oh, well, before we actually say what that amount is, repeated multiplication is exponentiation. So now that is going to give me 242.28. So end of year 3, I would have 224 times, then we'll just say 1.04 times 1.04 power 3. And that comes out to 251.97. If I went to year 10 years out, then it's going to be times 1.04 10 times on that original amount. So to the power of 10. Now, even at the end of year 2, then it's going to be $331 now, 0.57. Okay. So now if and I don't even know if the calculator will do it, but I'm going to try. I'm going to see if my calculator will actually do this. The book doesn't do it, but at the end of the year 535, then this would be 224 times 1.04 to the power of 535. And again, this is compounded. So I'm going to see what my calculator will do with this. 224 times 1.04 to the power of 535. All right, so got it punched into my calculator there. And hit enter. That's what I thought was going to happen. The number was too big. But in theory, that's what would happen here. Now, you need a calculator that is going to be able to handle this, and mine did not. Oh, wait a second. Hold on. Hold the phone. I thought my calculator should. Note, there was a slight mistake on my, see, I've got it right up there. So the top one was the original one I did. Notice I forgot the decimal point. All right, so I have corrected that. And boom. There's my answer. Remember the E is what scientific what notation? What did we say? $290 billion. Notice that is times 10 to the 11th. So that actually comes out to be basically, I could get my calculator to do it, 2.905 904588029 times 10 to the 11th. All right. Now, remember, if I move my decimal place this way, 1, 2, 3, 4, 5, 6, 7, 8, 9. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's put some parentheses. That is, matter of fact, I'm in billions here. Now, what did they do? They rounded it to what? 290 what? Billion. All right. So there was the king of Edward IV borrowing $224, but over 535 years, assuming 4% compounded interest. He did, in fact, would have, in fact, owed $290 billion. Power of compounding. All right.
Mr. Cunningham,
Yes, sir.
I'm sorry to interrupt. I gotta go take care of something really, really quick.
Okay. All right. Now, so let's make an observation about what we did here in terms of just a general formula we could cook up. It was principal, the original investment, times what? The interest rate, but plus what? 1. And then to the power of the time, and we put the time in years. That is, it compounds every year, what we call compounding annually. All right, so that is we're going to call A. And A is going to be my accumulated balance after a number of years. So that is, here's my A, $290 billion rounded. Principal times 1 plus, now that is APR, and it's going to stand for annual percentage rate. In our problem here, our annual percentage rate was 4%. And then to the power of Y. All right, so, and we have a compound interest formula for interest that is paid annually. We have built it right there. All right, so I'm going to turn the page. So I've got more room to write. I'm going to write that one more time. Your accumulated amount after how many ever years of accumulating interest will equal the principal times 1 plus what we're calling APR, annual percentage rate, and then raise that to the number of years. So again, your A is accumulated balance after Y years. P is your starting principal. APR is your annual percentage rate. And we always put that in the formula as a decimal. And Y is the number of years that you're going to have this investment, right? All right, so we've actually already seen, again, if I flip back just real quick, right here, where we calculated up that here was the exact amount of money that the King of England owed after 535 years and roughly $290 billion. All right, now again, this is, oops, too far. This right here was our,
I'm back. Sorry about that.
you're fine, compound interest formula. And this is for interest paid annually, or which annually means once a year. Okay. So now, there's nothing saying that you can only compound once a year. What if I decided to compound once every 3 months? And so I would have now my annual, you're always going to have an annual percentage rate, right? And that word annual means over once a year. But what I could do is I could compound it. If I said I wanted to do it every 3 months, I want to earn some interest. Then if I'm doing that every 3 months, I'm going to compound 4 times, or what we might call quarterly. And I could take that annual percentage rate and divide it by 4, figure out what that is as a decimal, and use that. So that's going to be our next formula. So it's going to kind of look like our original one. A is still going to be our accumulated balance after Y years. P is still principal. Times, I'm still going to have 1 plus that annual percentage rate, but I'm going to divide it by N. N is going to be the number of times I compound within a year. And then I'm going to multiply up top, that is in the exponent, that number of times how many ever years I have it in there. So this again is our compound interest formula. For interest paid in times per year. Now, everything else is the same as we had wrote out in the previous problem. The only new thing we have in here is n. And n is simply the number of compounding periods per year. All right. So let's look at a problem involving this formula. So let's say I deposit $5,000 in a bank account. So that's going to be my principal. And we've got an APR of 3%. So that's annual percentage rate. And we are going to compound interest in this problem monthly. All right. So, and let's figure up how much money would be in the account after 5 years. So question mark. All right, so let's figure it out. Our principal is 5,000. We have 1 plus. Now I've got an APR of 3%, so in decimal form, that would be 0.03. But what I now need to figure out is what's in. Since it's compounding monthly, then that is, how many times do I compound? In this case, if it's monthly, I'd be compounding 12 times. All right, so up top, it is going to be that number of times I compound times the number of years I'm leaving it in there. So that's going to end up being 12 times, and it would be for 5 years. All right, so this is what I want to put in my calculator. Now, these calculations with just a scientific calculator do get a little tedious because you have to do everything, what would I call by binary operations, just 2 at a time. You have to first divide these 2, then add the 1, and then raise it to the power of 60. That is 12 times 5, and then finally multiply it by 5,000. With the TI-30, you actually could enter this all in one shot. I'm going to use my TI-30 this time, not my TI-84, and put this in here as I see it. So that would be 5,000 times, and then it's got parentheses. Right. It's right above the 8 and 9. And then 1 plus 0.03 divided by 12, close parenthesis. Caret key is the exponent key, and it's right here. Now, I would just say to the power of 60, because that is 12 times 5. And hit enter. All right. That gives me Rounding to hundreds place, that is cents, 5,808.08. So that's how much money I would have after 5 years, 5,808.08. So I would have earned $808.08. Any questions on that?
I think I'm okay.
Okay, now we're gonna do the same problem. But let's not say assume, let's say if interest buddy, I'm in class, man. I can't play right now. If interest was compounding just at the end of the year, it's compounding. So we're gonna each year multiply by 0.03 times principal plus the interest earned from the last year. Then the formula, remember, looks like your principal times, and it would just be 1 plus 0.03, and to the power of, we're doing this for 5. So if I chunk that into the calculator, that's going to end up giving me 5,000. Darn it. $5,796.37. So if I take the difference, 5,808.08 minus 5,796.37. By compounding it monthly, I earned an extra $11.71. Okay, so the moral of the story, looking at this problem, looking at if I compounded it every month compared to compounding it just once a year, what we're taking from this is the more times I compound, the more money I'm gonna earn. So all right, what time is it? 8 o'clock. All right, now if I was kind of looking at percentage of how much my money increased by. What I'm kind of wanting to get to here is this. Let's flip back so I can make this observation here. This one right here, where I compounded just for the year. And this, so after 5 years, I obtained this amount of money. What I might call my yield, that is how much after 5 years percentage wise, did my money increase from my original investment? Might call it my yield, my percentage yield. If I'm just compounding annually, this percentage yield will be the same as my APR. That is, it'll be 3%. Calculate that. So if I took and see if I still have that, my absolute increase. So for here, my absolute increase would be $796.37. Now I'm doing it if I was just compounding for one, annually. That's how much I earned 5 years. Now, my starting principal was what, 5,000. All right. 796.37 divided by 5,000. Shoot. Oh, okay. All right. So what I wanted to show was this. Of course, this was figuring up my percentage increase after 5 years. And roughly, it's about 15%. If I divide that by 5, so I can figure up just after 1 year, I'm about 3%. If you take let's do it this way. I gotta turn the page, but I gotta remember the numbers. So seven. All right. So I want to keep with this problem. If I would figure up 1 year, compounding in 1 year, that's 5,000 times 1.03 first power. So let me figure that up. $5,000 times 1.03. $5,000 times 1.03. 5,150. Now, if I take that, which was my absolute increase, that is, what do you got now? Let go. $150 divided by my original investment. Divided by 5,000. It is exactly 0.03. So my yield after 1 year is exactly my APR. But if I would compound over 12 months, then that would be, so if we figure up just for 1 year, but compounding it every month, then I would have 1 plus, now it's 0.03 divided by what, 12, and then we're only doing it for 1 year, but we're compounding it what, 12 times, once a month. All right. So if I figure this up, That's gonna be 5,000 times 1 parenthesis 1 plus 0.03 divided by 12 close to the power of 12. I get $5,152.08. Now, which means I've earned $152.08 for the year. My original investment was 5,000. So that's going to come out to a little bit more than 3%. 152.08 divided by 5,000 is 0.030416. Now, not substantially more, but my point is, when I'm looking at my percentage yield, we're talking about relative change as a percentage. It's going to be exactly the APR if you're just doing it for compounding annually, but it's going to be more than the APR if you're compounding more than once a year. All right, so putting this all together, we're going to call this the annual percentage yield, which we will refer to as APY. This is the actual percentage by which a balance increases in 1 year. Okay. And as we saw from this example right here, it is the APR if the interest is compounded annually. It is greater than the APR if interest is compounded more than once a year. All right. So basically, we already knew we were going to make more money if we compound more than once a year. Now we can just phrase it as we're going to have a greater yield. And again, this, when we say greater yield, this is the percentage that I earn. All right, now that leaves us one last formula, and this one is a little squirrely mathematically. We have basically now two formulas that we have cooked up. compounding interest once a year. And then compounding more than once a year. That was 1 plus then the APR divided by the number of times I compound to the power of the number of times I compound times the number of years I have it in there. Now, incidentally, you can have a non-integer in here for Y. Let's say you only invest for 6 months. If it's 6 months, you would put 0.5 in for Y. Half a year. All right. So we already know the number of times you compound, the more money you're going to make. So I mean, we could take this to the extreme and say, let's compound daily. Then N is 365. So, but we could take it even a step further than that. We could do we could compound every moment in time, right? Complete interval, just not just a second, but literally every moment of time. It's what we call continuous interval. So there is what's called compounding continuously. So it's just literally always compounding. All right, so this formula, it's going to look a little squirrely. It's principal times, and I didn't want that parenthesis there. That is the letter E, small case. And up in the exponent is the APR, your annual percentage rate, times Y. And again, this is what's called the your interest formula, your compound interest formula, compound interest formula for continuous compounding. So what looks strange at first, obviously, is this E. It is a number. It's like pi. It's irrational. It's about, if we want to round it to hundreds place, 2.71. Now you can find it. Let's see here. There we go. All right, so on the TI-30 XS, if you start here on the left row keys, it's the third one down, it's the second function. And I'm going to hit that second function. Oops, got to turn this thing on. Third key down, and you'll see where it says E, and it's waiting for me to put a power in. I'm just going to put 1 and hit enter. And then you'll see that they're about 2.71, or you could even round it to 2.72. And that is Z on the TI-30. I believe you can find it here if you have an iPhone. I couldn't swear for a Android. I'm not familiar with them, but if you go to the calculator on iPhone and turn it sideways, you get a bunch more functions. And there should be And it's right there. You'll find e to the x. I'm gonna try to put it up there. So there we go. I'll let it focus. You can kind of see it. You see 10 to the x, and then right beside it, man, light is terrible. But you'll find an e to the x. Again, if you try it one more time here. And it's right there. I've got it to the left bar. There's one that says LN right above it. You have e to the x. So it's on the phone as well, at least on an iPhone. But if I went back and just said, as an example, I've got an account. I got $100, and that's my principal. I got an APR of 8%. And I'm going to leave this in there for 10 years. And that is my why. But I'm going to have continuous compounding. Go to this formula. So to figure out how much money I would have after 10 years, I would put in $100 times, you punch the number E, then you want to, and again, like on the phone or on the TI-30 XS, when you hit that key, the next thing it wants is what to put in the exponent. And in this case, what are we going to put? 0.08 times 10. That's up in the exponent. And so we just plug that in there and do the calculation. And rounding, that's going to come out to $222.55. Now, book doesn't do this, but I'm just curious, what if we just did simple? And that would be $100, not simple, but just compounded for 1 year. That's it. Then that would be 1 plus 0.08 to the first power. So if we just did it that way, that'd be 100 times 1.08 to the power of, in this case, 1. And something went amiss. Oh, let's do it to 10 years. That's what the problem was. I'm trying to compare these. I just did it for 1 year. There we go. 100 times 1.08 to the power of 10. So that would be $215.89. Just going rounding. So again, you're going to make, if I did it even compounding it 12 times a month, it would still be less than $222.55. So all right, I know we're a little past time for the class, but we've had some early nights too. So I'm going to do one more problem like you'll see in homework here. We can take these formulas and figure up different parts of it. That is this, and this is a common thing to do. So let's say I want to, I want to invest money in an account. I know that it has an annual percentage rate of 3%. All right. I'm going to compound monthly. And I'm going to do that for 18 years. i.e., I've got a kid. So I'm going to, as soon as they're born, I want to invest money for college, for their college. So I'm going to put it into this account. APR is 3%. I'm going to compound it monthly for 18 years. So what I want to know is how much do I invest, right? Knowing that I want my accumulated balance after 18 years to be $100,000. Okay. So, so how much money do I have to put in there in order to have the $100,000 under these conditions? So again, recollect that the formula here is principal times 1 plus APR divided by the number of times compounded to the power of the number of times compounded times the number of years. All right, so we're going to do a little algebra here, because what I know is I know A, I know my APR, I know N, I know Y, I know everything but P. P is the part I'm actually looking for here. And all of this, it's times, all of this is one term. And remember, a little algebra rule for equations, I'm allowed to divide both sides of an equation by the same thing. So I'm going to manipulate this equation by dividing both sides by all of this. Now the goal is, if I do that, these two are going to cancel out. But what I do to one side, I got to do the other. But what that sets up is I now have, I've just manipulated this formula algebraically a little bit. So I have isolated P. Now I can plug in the numbers that we have. We want to have my accumulated balance after 18 years to be $100,000. And I'm going to divide this by 1 plus. Now the APR is 0.03. I'm compounding monthly, so 12. And I'm doing this, again, 12 times for 18 years. So it's a matter of then just chunking all this into my calculator. And that's going to give me, they're about what then? $58,314.11. So that's what I would have to put in there in order to get to $100,000. But I can certainly do that calculation. All right. So that was a lot of stuff.